All right. Now we're going to go on to torque. So, torque is the rotational analog of force. So, just like a force is something that can alter the translation of an object, a torque is something that can affect its rotation. And the definition of torque is the cross product of a distance vector from the point of rotation uh, and the force that's applied. And since we're typically not just given ij and k hat vectors to cross and do this explicitly, we've come up with several clever ways to evaluate this cross product. They're equivalent, but sometimes one is more useful than the others. So, the first way, the most direct way probably, is thought of as the perpendicular force method of torque. So, if you think about this object right here as like a rod or a door, the thing that is causing this rod to rotate by this force, it's not actually the whole force. It's only this part, which we call the perpendicular part. So, by doing some clever tip to tail addition, we can see that I can split the force into two parts, like this. And we can see that if we think about this as just the blue force being applied, well, that's the thing that's causing it to rotate. So if we just think of the blue force component, that's what's actually causing rotation. And we call that the perpendicular force component. So if you can just break all forces into perpendicular parts, then we can just find the torque by multiplying the distance that the force is applied by that perpendicular force. Because again, this green component is really not doing anything for the rotation. So conceptually, we'll just do an example here. A wheel is allowed to freely rotate about its center of mass, which situation results in a higher torque on the wheel. So again, the forces are the same and the distance is the same. So it must be something about these forces that is causing a difference in torque output. And well, there is. And given that this is about perpendicular forces, that's 100% what it is. So if I split these vectors up with a nice little tip to tail addition, we can see that clearly the first case has more of the force vector oriented vertically. And that's what's actually causing the rotation. Because again, if you think about spinning a bike tire, you got to press perpendicular to the tire. So it's only the blue part of the 50 newtons that's causing rotation. And since it's the same force along the hypotenuse, well, if A has a longer blue perpendicular component, it must be generating more torque. So again, it's case A because F perpendicular is larger. Is larger in case A. Next, we can move down to the perpendicular distance method, also known as the lever arm. So here we said, okay, let's just split the force into the perpendicular part. Well, same thing can be done with the distance, and we call that the lever arm or the moment arm. So if instead of wanting to split the force up, so again, like we did before, what we would have done before is we just kind of split the force F like this and just found the perpendicular part. We can also just split the entire distance vector and sort of try and find how long that lever arm is. So again, in this case, you could just utilize it by saying, well, if the rod's the total distance, we could copy that over like so, and we could solve for that lever arm. And it always meets the force at a right angle, because that's how you get the quickest way from a line to another line is just perpendicular. There's a classic example of lever arms. We have to talk about doors. It's a classic. So let's just draw ourselves two cases here. So explain why doors are placed, why the knobs are placed far from the hinges. So let's just draw ourselves a little hinge here and here. And then let's pick different places to apply the force at. So we're just going to say that this right here is going to be our axis of rotation. So let's just place some forces. So let's say for our first attempt at pushing the door, we're going to apply a force F right there. And then for our second force F, let's place it over there. So in each of these cases, the force is already perpendicular. So the lever arm is just going to be there for the shortest horizontal distance from the pivot point to that actual force. And that's going to be given by this purple line. So we can see that in the first case, if you're pushing close to the hinge, you got a very low lever arm. This dotted line is very small compared to the other case. So why doorknobs are placed far from the hinges is because if this is the lever arm and this is the lever arm, placing the handle far from the hinge creates a larger lever arm. Larger lever arm. So again, that's why it's easier to open a door when you push far away, because you're increasing that lever arm. Or if we just kind of want to compute it and don't want to get fancy with it, we could just apply the direct definition of the cross product, which just says to find the cross product's magnitude, just multiply the two lengths together and tack on the sign of the angle between the vectors. So in this case, you can just think of copy pasting this R over here, and we can see that the angle between them is going to be that theta. So be careful. Just because you have a theta in your diagram does not mean that that's the theta that goes in there. It can often not be. So that's why actually looking at the two vectors together, making sure they're tail to tail like this, make sure your angle is named correctly. So let's explain why the definitions of torque are equivalent. So the thing we know is as sort of our base is that torque is equal to RF sine theta. And we're going to show that this is equivalent to the other two methods. So line by line, I'm just going to work out symmetric sort of derivations here. So first thing we're going to do is, the first thing we could do is we could associate the force with the sine theta. So we could tack on the sine theta to the force itself. And what is that? Well, we can draw ourselves a diagram. So we can give ourselves a force, and we can give ourselves a distance vector. So we're going to say that this is F, and this is R, and this is theta. And before I lose all this lovely stuff, I'm just going to copy it on over, because we're going to need it later. So what is F sine theta? Well, F times sine theta would give the length of this purple line right here. So this is equal to F sine theta. But if you examine what this is it meets at a right angle right here. So this is actually just F perp. It's the part of the force that's actually causing rotation. So this is the same thing as just R times F perpendicular. So that shows that definitions 1 and 3 are equivalent. Now let's handle the lever arm case. So you can probably guess what we're going to do. We're just going to say, okay, let's attach the sine theta to the R instead of the F. So that means we need a right triangle with R as the hypotenuse. And that's just going to be this triangle down here. So it's going to meet the force at a right angle. Okay, so that's interesting. A force meeting a line to the displacement vector at a right angle. Well, that's the definition of a lever arm. And notice that the length of that line is exactly r times sine theta, which is the same thing as lever arm. And that's the same thing as the force times r perpendicular. Why do we have 3 definitions for torque, or 3 methods for doing it? Well, depending on what your picture looks like, one of these might be more effective than the other. But just for the sake of just practicing, we're just going to show that in practice, you can use any of these and always get the same answer, although some may be more easy to accomplish than others. So we got a force of 100 newtons, so that's F, is applied at the end of a 4-meter long bar, so this is R, at an angle of 30 degrees below the horizontal. So not perpendicular, so we can't just multiply. So the answer is definitely not 400. Find the torque caused by the applied force, and we're going to go through 3 different ways of doing it. So perpendicular force, lever arm, and angle between. So first, let's just draw ourselves a diagram that we're going to do a couple times. So give ourselves a bar, and we'll exaggerate the length of our force. Then we'll give ourselves a nice little horizontal for our angle. And this is 30 degrees. Okay. And then I'll just copy paste that. I'll just copy paste that down below 2 times so that we can use it later. Okay. Perpendicular force method first. So, well, you can see that if this force is acting at the end of this rod, the only thing causing rotation is the downward component of the force at that location, denoted by the green line. So if this is 100 newtons, the part of the force actually causing the torque is just going to be 100 times sine of 30 degrees, because the green line is across from the 30 degrees, so that's just 50 newtons. So even though the force is 100, the force that's actually causing the torque, well, that's only 50. So torque is just going to be R times F perpendicular, which is equal to, well, the force is 4 meters away, and it's worth 50 newtons. So that's 200 Newton meters of torque. Not joules, even though that is equivalent unit-wise. Lever arm. So instead of dealing with the perpendicular force component, let's deal with the perpendicular distance component. So I want to find the shortest distance between the distance vector and the force vector. So it has to meet the force at a right angle to be the shortest distance. So that's denoted by the purple line. And this meets at a right angle. And this distance we said is 4 meters in total. And now just by applying some trig relationships, so if I drop another line into this here and make a right triangle, we can see that if this is 90 degrees, this must be 60 degrees, which means that this angle right here is also 30 degrees. So that means the purple line is just going to be 4 times sine 30 degrees, which is equal to r perpendicular, which is equal to 2 meters. So in this case, torque is equal to r perpendicular times F, which is equal to 2 meters, times the full force of 100 newtons, which is equal to 200 Newton meters again. All right. So now, notice that it was the same answer, which is always good. That we split either the force or the radius vector, but not both. Just split one. And now the angle between method. So this is probably the easiest one for this because it's easy to see that if my bar, so if my pivot's right here, my bar is just going to be horizontal. So I can just copy paste that bar up a little bit. And I can easily see that the 30 degrees is the angle trapped between the two vectors. So if this is 4 meters and the force is 100 newtons and there's a 30-degree angle between them, the torque is just going to be 100, or it's going to be 4 times 100 times sine 30 degrees, which is equal to 200 Newton meters for the last time. So again, in practice, if I were to do this, I probably would have done the first method of just finding F perpendicular, although a close second for me is just seeing that R and F have a 30-degree angle between them. And again, it's important that your vectors are tail to tail, or else you'll be off by 180 degrees. Or the supplement, sorry. All right. Now on to static equilibrium. So just like before with forces, where if something is at constant velocity or at rest, all the forces must balance. The same is true about the torques if it's in static equilibrium. So it can't rotate either. And with the force, we know that the forces in the x direction and the y direction balance, so that's two equations there. But the torque, that has to be true about any pivot we could possibly want. So it doesn't matter where we measure torques from, they always have to balance. And this is actually a really useful problem-solving tool, because given the fact that torque is equal to RF sine theta, if R is 0, torque is 0. So if there's any nasty forces we're trying to eliminate in our problem, we should take the torque about the point where they're acting, which is interesting. So first, we'll deal with a simple balance with no angles. So we got a seesaw of length L is pivoted about its center of mass. So it's going to be pivoted about this point right here. And it's of length L. Alice has a mass of 50 kilograms and Case has a mass of 200 kilograms. If Alice is sitting on the left end of the seesaw, find where Case needs to sit in order for the seesaw to remain at rest. So we have a light girl and a heavier boy. So in this case, we know that just thinking about torque, so since torque, everything's perpendicular here because their weight forces are going to act directly down, which I'll definitely draw first just for illustration. So he's going to have a pretty big force and she's going to have a not as large force. So given the fact that torque is equal to R perpendicular times F in this case, because again, since F is already perpendicular, it's just going to be RF for this problem. If Alice is lighter, that means that she definitely has to be farther away from the center of mass to generate the same torque. So we need to find what this equilibrium position is. So let's see what we're given. Alice is sitting at the left end, and it's pivoted about the center. So the fact that it's pivoted about the center means we don't even have to look at the fact that the seesaw's weight could be a factor. So it's not, so we don't have to deal with that. So Alice is sitting at one end of the seesaw. So if the seesaw has length L, she must be a distance of L over 2 away from the pivot point. And we do not know anything about how far away Case is. So let's just go down here and call this X because we don't know what it is. So we need to find how far away is he if it's not actually if it's not rotating either way. So the fact that the torque in this scenario is just going to be their force multiplied by their distance from the pivot means that, well, we know that Alice's weight causing the torque is just her mass times g, and Case's torque is also caused by his mass times g. So all we can do is we can just set up some torques. So we know that the amount of torque rotating the system counterclockwise has to be equal to the torque rotating it clockwise. So again, if we think about just pressing down at each of those points, Alice is trying to get the beam to rotate counterclockwise, and Case is trying to get it to rotate clockwise. But those two have to exactly balance. So we basically have this. RA times MA times G is equal to RC times MC times G. Because again, the torque is just going to be their distance multiplied by their force. G cancels, which is interesting for a lot of these static equilibrium problems, that it doesn't even matter what planet you're on. And solving this out, you can see that if Alice is at L over 2, and Case is at a distance of x, you can see that x is just going to be equal to MA over MC times L over 2. And given the fact that Alice is 500 kilograms and Case is 200, means that this fraction is a quarter. So the answer is L over 8, which in hindsight should make sense. So Case weighs 4 times as much. So he must be 4 times closer to the pivot. Because again, or maybe it makes more sense the other way. If Alice is 4 times lighter, she has to be 4 times farther away to generate the same torque. So same thing. Very classic example. This is definitely you gotta know it sort of thing with static equilibrium. Is the case of the seesaw. And now we have a more involved seesaw. Don't ask me how I even thought of the inspiration for this problem, as someone who doesn't watch old cartoons, but for some reason I'm thinking of a classic scenario in which Tom and Jerry are beefing as per usual, and Tom and Jerry are setting up traps for each other. So we're saying that Jerry, the mouse, basically sets a box of catnip at the end of a rod, a steel beam that's sort of precariously balanced over a cliff. And Tom, being a dumb cat, is going to walk across the beam and attempt to just take the free snack at the end. But if Jerry's calculations are right, there exists a certain point where Tom's going to walk far enough that he's actually going to generate enough torque such that the whole beam falls over. But to start, there is this sort of counterweight that he placed on there. So let's just fill in some values before we start. Just plugging and chugging here. So this is 100 kilograms. So there's a 100 kilogram counterweight placed on the left end. There's a 5 kilogram catnip treat basket. Tom's mass is 20 kilograms. And we know that it's not pivoted about the center of mass in this problem, but instead it's pivoted about a point 1 meter away from the end of a 5 meter rod. So maybe we can put some distances in for everybody as well. Once we get the forces. Also, the beam has mass. So the beam is 30 kilograms. And that definitely will come into play for this. So, starting out, we can draw ourselves all the forces And if we do our torques about the pivot, this means that all our forces we have to consider are just weights. So we have a huge weight force coming from the counterweight. Then we have Tom's weight, and then we have the little weight of the little basket right here. But we also have the fact that the beam has mass. So if something has mass, we always approximate its weight force at the center of mass. That's what center of mass means. It's the point where we can approximate the mass at. So this whole beam is equivalent to just there being a 30 kilogram dot right down the center. Because again, we're given that it's uniform. So now we just got to compute some forces here. So the fact that weight equals mg, using g equals 10 meters per second squared, the counterweight is 1,000 newtons. The beam is 300 newtons. Tom is 200 newtons. And the catnip is 50 newtons. And right before we're ready to solve for everything, where we're eventually going to figure out how far Tom can actually walk before the beam falls over, let's get our distances in, because torque is not just about force, it's about distance as well. So let's find our distances. So the first one's the easiest. So this is, we're given that the beam is placed, or the pivot is 1 meter away from the edge of a 5 meter long beam. So this is 1 meter. We'll come back to the center of mass. Tom, we have no idea how far away from the pivot he is, so we're just going to call his distance x. And the catnip is all the way on the right end of the beam, so it's going to be 4 meters. Not 5, because the whole beam is 5, so he's just the remainder of the way over. Then for the center of mass, we know that the center of mass is going to be 2.5 meters away from the left end of the beam. So that must mean that this distance right here is just going to be 1.5 meters. Because 1 plus 1.5 equals 2.5. Now we're actually ready. So at the moment when Tom finally slips, we're just going to set the counterclockwise torques equal to the clockwise torques about the pivot point. So basically, this is a battle between the counterweight and everything else. Because the counterweight's driving it counterclockwise, and everybody else is driving it clockwise. So, once again, since everything is perpendicular here, we can just say that torque is going to just be equal to force times distance, which is going to be equal to all the weight times the distance for each, because the weight force has already been calculated. So it's just newtons times meters. So clockwise, or counterclockwise. So we have a 1,000 Newton weight acting 1 meter away from the pivot. Then we have a 300 Newton beam whose weight force is acting 1.5 meters away from the pivot. Then we have a 50 Newton weight force acting 4 meters away from the pivot. And lastly, we have 200 newtons of Tom's weight acting a distance of x away from the pivot. So now we'll do some simplifying. So we're just going to have 1,000 Newton meters of torque is equal to 450 Newton meters of torque plus 200 Newton meters of torque plus 200 times x, where x is Jerry's distance from the pivot. So we can solve, and we will get x is equal to 650 subtracted over, we get 350 over 200, which is going to be equal to 1.75 meters. And just to make sure that's actually the answer we want how far from the edge of the cliff. And yeah, that's the pivot point. So we can see he's not making it much farther than the center of mass of the beam before he actually falls down like that. But as is the nature with these cartoon characters, they're always foiling each other's plans. So suppose Tom figured this out. What total mass could he replace the counterweight with such that the beam doesn't tip and he's able to actually get his tasty treat? So in this case, we still got our little pivot, but now we have a bigger counterweight. So I think we could agree that if we put a larger weight on the edge, there's more balancing torque, so he could make it further. So how far or how large do we need it so that he can make it all the way to the other end? So the thing that's the same is the beam's weight of 300 newtons is still going to be 1.5 meters away from the pivot. But then we want him to make it all the way to the right end. So not only do we have the little catnip at the right end, we also have Tom as well. And if we look at our previous free body diagram, we see that Tom was 200 newtons and the package was 50. So we have 250 newtons of weight at the left end of the rod now, which is 4 meters away from the pivot. So now we just set the torques equal again. So we don't know what this is, so we're going to call it W. So the counterweight times 1 is equal to 300 newtons, 1.5 meters away, plus 250 newtons times 4 meters away. So that means our mystery weight force is 1450 newtons. And dividing by G equals 10 meters per second squared, we get the mass required is 145 kilograms. So much larger than the 100 that was originally there, but not impossibly so. But why would you ever do it this way? There's simpler ways that he could have gotten to the other edge. So assuming he couldn't just like pull the entire beam to the other side, provide another way in which he could change the setup in order to make it without falling. Well, the simplest way is to move that pivot point. So if you shift the pivot point to the right, so if you shift the pivot right, more balancing torque is provided. More balancing torque is provided by the weight. Because if we put that counterweight all the way on the left end, assuming it's large enough, like it's over 200 pounds, it's hard to move. Well, you could just move the pivot. So again, if you double the distance that the pivot is, that's gonna increase the amount of torque provided by the same force. And also that's going to decrease the torque provided by everything else. So a question that I didn't ask, but I definitely could, would be where can you place this pivot such that without any other modifications it works? So instead of knowing this pivot location, we could solve for where that is. A little bit more algebra, but it works out. And just to finish on a little lighthearted one, how was Jerry, a mouse, able to set the trap without falling? Well, Jerry is a mouse, so he has very little mass. his small mass did not generate enough torque to tip the beam. And that's another thing we could ask is, what is the maximum mass Jerry could be to set this by walking on it? Did not generate enough torque to tip the beam. All right, and our last equilibrium problem, you know that any scenario in which there's a sign involved, we have to shout out Michigan legend Connor Stallions. So we have, in the setup pictured below, a sign of mass 30 kilograms is suspended 2 meters from the left edge of a uniform beam of mass 50 kilograms and length 10 meters. So we know that L is 10 meters, and the mass of the beam is equal to 50 kilograms. So not massless. On the right end of the beam, there is a supporting cable that makes an angle of 30 degrees with the beam. The system is in equilibrium. Okay, this is another classic torque situation. So, we're going to draw a free body. So first, we're given that it's in equilibrium. So the fact that this system's in equilibrium means that this sign is not falling, so the tension in this cable must be the same as the 300 newtons of weight of the sign itself. And since tension always points along the rope, that means that the sign's weight force is going to be whatever this is, the same thing as this blue arrow down here, because we're just drawing it on the beam. So that's going to be 300 newtons. And we're also given that the sign is 2 meters away from the left edge of the beam. So D is equal to 2 meters here. Next, the beam is not massless. So right down the center of mass of the rod, there's going to be 500 newtons of weight. And if the beam is 10 meters long, the center of mass of the uniform beam is just 5 meters along there. Then we have a tension force at the left end of the beam. We do not know that, so we'll just call that Ft. But we do know that the tension force is acting at the right end of the cable here, so at least we know that the distance is going to be 10 meters. And then the force that we always forget about, but is definitely still here, is there's always a force when two things are in contact. That's the normal force. So the beam is in contact with the wall at that point, so we're just going to draw in some direction a force caused by the beam, a normal force, a contact force, or it's commonly written as a hinge force. Again, I don't know if the direction of this is right or not. We may find out later. But I do know there is a force there. All right, quite a lot going on. So if we look down here, we're going to solve for the tension in the cable and then eventually solve for the contact force. So first thing, what point should we choose as a pivot point? So rule of thumb is choose the point you know the least about. Because if you pick the torque about a point, that eliminates all forces there. So it seems smart to pick our pivot point to be the hinge. So we should sum our torques about the hinge, because that means that the torque caused by the hinge is equal to 0. So it eliminates the hinge force. Another good candidate would be to sum around the right end of the rod to eliminate the tension force, but we just know so little about the hinge force right now. We don't even know the angle it's acting at. We know less about that. So it makes sense to do the hinge first. Solve for the tension in the cable. So, since I don't know the hinge force, I can't just set the forces equal to 0. Because I don't know exactly what the hinge force is bringing to the party. So this must mean that I can eliminate it by summing up the torques about the hinge and setting it equal to 0. So the sum of the torques about the hinge have to be equal to 0. So what this means is that the clockwise torques have to sum to equal the counterclockwise torques. So in this example, since I'm summing about the hinge, that eliminates the hinge force. So what we have is two different weight forces, the sign and the beam, trying to rotate it clockwise. And we have a tension force who's at least partially attempting to rotate it counterclockwise. Because again, if we look at our tip-to-tail addition model for this, we can see that this part of the tension force is actually what's causing it to rotate. So first, we can actually explicitly calculate the left side of this. So we have a 300 Newton force of the sign acting 2 meters away. And we also have a 500 Newton force from the beam acting 5 meters away. And then for the right-hand side of this equation, well, we can see here that using a torque argument of your choice, we need to figure out how the torque relates to the tension force itself. Because this angle in here means it's probably not just going to be tension times distance. So we have our choice, either perpendicular force, either lever arm, or just product times angle between. And in this case, we can see that it probably makes sense to do the perpendicular component or the theta between. But so if I, so we'll just clean this up a bit, just to look at our picture a bit more. Okay, so we draw ourselves a horizontal line right here. That's going to meet us at a right angle with this component right here. So if this angle is theta, that means that this angle is also theta. So what that means is that redrawing our triangle down here, that the perpendicular component of the force this perpendicular force component is just going to be just the force times sine of theta. Because again, if this angle with the horizontal is theta, 30 degrees. So if this is 30 degrees, this must also be 30 degrees. So this is just going to be ft times sine of 30 degrees. So we can just get that that's going to be equal to the force that's causing the torque, which is not entirely ft, it's ft sine 30, times 10 meters, which is how far away it is, because it's all the way on the left end of the rod. So solving this out, you'll find that the tension force is equal to approximately, and I do actually need to just recheck my value right here, 620 newtons of tension in that cable. And again, you can probably tell why I chose a 30-degree angle here, so it made that sine part, at least that is going to work out. Because you get 3,100 divided by 5. All right, now you know what was coming. Solve for the magnitude of the contact force. So now we know everything except the contact force, because we just said, so we knew the weight of the sign. We knew the weight of the beam. And now we even know the tension. So now we just balance forces out. So we know that the sum of the forces in the x direction has to be equal to 0, which means that the sum of the right forces equals the sum of the left forces. And acting to the right in this picture, it's just part of the hinge force. So we're just going to have part of the hinge force acting to the right. And then acting left, well, not this weight, but yeah, part of this tension is. So we have 620 newtons of tension, but attach a cosine 30 to extract the part that's acting in the x direction, and we just get a not as nice value as last time of 537 newtons. Not our answer, because that's only a component. Now we got to play the game again, but in the y direction. So we know the sum of the up forces are equal to the sum of the down forces. So the upward forces in our diagram, well, we have part of tension and the hinge force. So we have 620 sine of 30 degrees plus the hinge force in the y direction equals all of the forces acting down, which is 300 newtons and 500 newtons. Because again, we have two different weight forces acting down, so both of them combine. And 620 sine 30, that's actually a decent number. So that actually works out. If I ended up getting a negative answer instead, that would mean I just got my directions wrong. But this is going to be 490 newtons. So if you got a negative, it just means you picked the direction of the force wrong. So my force is actually up and to the right, as I originally guessed. So again, our answer is just going to be 800 minus. So 800 minus that 620 divided by 2, which is 310, 490. All right, we actually want the magnitude of it. So it's time for some vector addition. So we have 537 newtons to the right, and so 537 newtons to the right, and 490 newtons up. So the resultant is just tip to tail of that. It is a right triangle, so we can just shortcut and do a little Pythagorean theorem and find that the hinge force is just the square root of the sum of the squares. And that's just going to be equal to 727 newtons. And again, if you use different G or different things like that, you will get slightly different answers than me. But the method is what's important. And then we'll finish with some concept. Conceptually, explain what will happen to the required tension in the cable if the sine is replaced with a heavier one. Okay, this is probably the easiest one to think about. So this is just saying that if we go back to our diagram, what if we just replace this with a very, very large sine? Well, that's just going to create a much larger downward force. Thus, the tension force needs to increase to balance the increased weight. So, just given a sketch of the full sentence answer here. So, we know that the torque. So, what's happening is mg is increasing for the sine. So, that's going to increase the clockwise torque of the system. So the counterclockwise torque about the hinge must also increase to balance it, thus Ft must increase. Because now there is a larger torque for the tension to balance. Now the sign is moving closer to the hinge. Well, the fact that everything's still perpendicular means that it's still just going to be force times distance. So what's happening is you're getting a less lever arm in this problem. So that lowers the torque it generates, meaning the counterclockwise torque to balance it also has to lower, so tension must lower. Because again, just thinking about this, just with a picture, if our sign's originally here, and we move it over here, well, notice the lever arm has significantly decreased. Now we have an interesting one. The cable angle is increased. So let's think about what that means. So instead of going at 30 degrees, maybe we're going at 60. What does that do to our system? Well, sometimes the best way to analyze a system like this is to almost over-exaggerate the change and see what that does. I'm not going to go all the way to 90 because we can't be sure that won't just wreck the system in some way. Spoiler, it actually won't, but let's just pick a very, very large angle here. And we'll just call this some new angle, phi. Well, what causes torque? Well, torque is going to be equal to RF sine of the angle between. Or, this is the same thing as R times F perpendicular. So what's happening now is by changing the cable, what we've effectively done is we've just changed how the tension force distributes itself. So now the tension force is much more vertical. So what this means is that even though it's the same force potentially, it generates more torque because more of it actually goes in the vertical direction. So in this problem, we have so what happens is sine phi actually gets increased, which would increase the amount of torque generated. So this must mean the tension force must decrease to generate same torque. And again, I like to think of this as almost like getting the most bang for your buck in this situation. So if your angle is very, very steep, what that means is that much more of the force is actively being used to actually rotate the system. So that means much less total force is required to generate the torque you need. Because if your angle is much steeper, well, you only need this component's going to be much longer. And again, compare that to a case like this. Even though it's a very large force, there's barely any of it that's acting in the vertical direction. So that's why making this vertical like this actually decreases your required tension, because you're getting much more torque for lower force. So this kind of shows the three things that affect torque. So force affects it, distance affects it, and the sine of the angle between the force and the axis. So I really like this question, but that might just be because I wrote it. So that should be a pretty good basis for static equilibrium. And then we'll start rolling into the more interesting case of unbalanced torques.